So our next speaker is Dr. Sassan Ahmadi from Mavenir. He's the VP of Technology. We'll be talking about Open RAN, cloud native, disaggregated intelligence service space, scalable RAN architecture of the future. Just to let you know, Mavenir, we had speakers from Mavenir in the past. I'd like to thank the company and the leadership. I met them in Mobile World Congress. So Dr. Ahmadi is a renowned visionary technical leader, experienced with 35 years in design, implementation, standardization of advanced wireless cellular technologies. He had previously held positions, Xilinx, Apple, Intel, Nokia, authored 3 recent books on advanced wireless communication, several book chapters, has more than 100 patents. He also teaches at Electrical Engineering Department of Stanford. So with that, Sassan, you can take it over now. I just want to introduce you. Thanks.
Okay. Thank you.
So you have about 20 minutes, and then I'll ask questions after that. Thanks.
Sure. Thank you so much. I would like to talk about, again, Open RAN. Many people talk about it, so I try to avoid, things that, have been talked about earlier. This talk is about where we are and where we are going. So about cloud native, disaggregated, intelligent, and service space and scalable RAN architectures. So we talk about Open RAN from concept to materialization, and then intelligence in RAN and cloud native Open RAN and evolution towards 6G. So just to give you, a very short background about RAN, we started from traditional RAN, in earlier generations of the wireless networks where hardware was custom hardware, software and hardware were proprietary, interfaces were proprietary, and actually a handful of equipment manufacturers provided solutions to the operators. Then we moved to 5G. We disaggregated the base station, and so now we have a central unit, we have a distributed unit, we have a radio unit, and then we also virtualized RAN, so softwareized. So we decoupled software from hardware, and we started using CUTs or commercial off-the-shelf hardware platforms to run RAN software. But this does not actually constitute an Open RAN because it is still proprietary, uses proprietary interfaces. So the Open RAN concept from ORAN Alliance was not only the disaggregation, was not only the virtualization or decoupling of the software and hardware, was not only decoupling of the control plane and user plane, but also actually defining open and standard and interoperable interfaces so that multi-vendor solutions, can be possible. And so this is where we are, and we are moving toward yet another architecture which actually uses public or hybrid or private clouds for deploying part of the core and RAM, and then we have virtual cell site router co-located with the DU, and then we are using open interfaces, and so this is going to be the as at least our vision, the architecture of the future. And this is this already actually is being used in deploying some of the operators' current deployments, like the dish networks. So Open RAN represents a disaggregated, fully virtualized, and intelligent RAN architecture with open interfaces that's scalable and cloud native. Now, in terms of RAN architecture, again, we discussed this, we disaggregated RAN, we decoupled the software from hardware. We decouple control plane from user plane. These all happen in 3GPP. And then ORAN started adding some new components, like near real-time break that people talked about it. Near real-time break has interfaces with the RAN components. And these interfaces are through some standardized APIs. And then there are some X apps, so applications that run on top of the platform. And these applications can be provided by the third party, and they comply with the standardized APIs. And then we have this service management orchestration, which includes a non-real-time break, and that is connected to the rig. And it has its own APIs. We call it R1 APIs, actually, and then R apps for different applications. And operators can actually, based on these different applications, differentiate their networks. And SMO further includes performance monitoring, fault alarm monitoring, configuration management services, slide management, and etc. So we collect input. In these inputs are in the form of KPIs, performance management, events, fault alarms, and so forth. And then obviously from different parts. And then we have the configuration management that actually is provided to the different disaggregated nodes. And obviously, we have two ways of communicating with the RUs. One is at the management plane. One is direct management. We call it hierarchical. And there is one through the DU, but which we call it hybrid. So, and then, you know, we have the OCLOT, and that is controlled actually through the O2. So the SMO is typically in the regional data center. The near real-time break and part of CU are typically at the edge of the cloud. And then you have the DU and RU typically at local data centers and sites. So people talked about it just briefly. The near real-time break and real-time break, they are for different purposes with different timing granularity. The non-real-time is a granularity of more than 1 second control. The near real-time is between about 10 milliseconds and 1 second. And then you have the real-time, which is the scheduler that sits in the DU, actually, which has the granularity of less than 10 milliseconds. And non-real-time break actually sets programmable policies, objectives for radio resource management of the UE, cells, slices, flows, and etc. And then you have near real-time break that controls the RRM for the UEs. And then you have open interfaces that, you know, people talked about it. And obviously there are FCAPs, or fault configuration, accounting, performance, and security information that are exchanged actually between, you know, these different control nodes and the actual, nodes in the architecture. So again, this is just, you know, a lot of effort ORAN actually has put in the definition of the open front hall interface. That it has 4 planes. Control user plane, synchronization plane, and management plane, as we discussed. Then you have the A1 interface, and then, you know, there are other interfaces that, you know, ORAN has defined in order for the whole system to work. These are more perspective into the RAN intelligent controllers, as well as the SMO and the type of functions that they do. So cloud native network architecture, it's very important and interesting topic that, you know, operators right now are moving toward deploying part of their network in public, hybrid, or private clouds, depending on the use cases. For example, for a non-public network or an MPN, you may prefer a private cloud, enterprise cloud, or a hybrid cloud, or even a public cloud. for like, a macro, deployment. These are the operators that have already committed to deployment of part of their networks over hyperscale cloud providers like AWS, Microsoft Azure, and Google Cloud. And obviously, telco deployments are moving to fully virtualized, that we talk about it, and containerized on the private public clouds. Operators are differentiating their networks by offering unique services. And this trend reduces the operator total cost of ownership and allows faster deployment and upgrade of the network entities and features. And Mavenir actually provides cloud-native RAN, core, edge, software, and hardware solutions. So one example is the Dish network, that we are working with Dish. Several companies are working with Dish. Some companies are providing RU, some companies are providing the MEC, UPF, CU. We provide DU over AWS outposts, and these are different, like, cloud zones or and data centers with different actually quality of service and quality of experience and security and features that they provide, so that different parts of the network can be accommodated and requirements can be met. So this reflects actually where we are going in terms of the network architecture.
So, Sassan, you have about 5 minutes.
Okay, and so just this architecture is very friendly to machine learning and artificial intelligence. In fact, 3GPP has already defined this network data analytics function for collecting event, and it has exposure to the core network, collecting metrics, logs, alarms, to actually process end-to-end quality of service, smart paging, etc. And then obviously non-real-time break and near real-time break provide intelligent control at different timing granularity actually over the RAN network. And the last slide is about, like, the perspective to the future. So you have this intelligent industrial and business services, manufacturing, transportation, security, etc. And then you have this cloud native, disaggregated, virtualized radio access network, which is further, made intelligent. And, you have these different apps that can differentiate your networks. These apps, work on different parts, on different features like traffic management, KPI prediction, load management, distribution, etc. And then you have several use cases that you can actually enable automated and automate, like network operations, network planning, service experience, and all those things that can be materialized based on this architecture. Thank you.
I have one or two questions maybe able to answer. One of the questions you may already have answered: which operators are using cloud native ORAN? I think you probably answered that, right?
Yeah, I provided actually a reference. There is a more updated version of that reference that shows the operators that have already committed actually to Open RAN, and some deployments are happening, including Dish Network, Rakuten, and we have Vodafone, Deutsche Telekom, etc. Yes.
Okay, so there is a better TCO to directly attach RUs to DUs in a DRAN case. DRAN case? Okay. Is this scalable if a single server has to handle 10 to 20 ORUs, frontal switching I thought is the default choice.
Yes, it is a scalable. So this question was asked from one of the speakers before that, like, how many DUs you can attach to a CU or how many RUs you can attach to a DU. The scalability comes from the fact that you can scale the processing platform, right? So you don't want to over-engineer because you have cost and complexity and power consumption and all those requirements in mind, but you scale the processing platform to be able to handle the front haul bandwidth, the configuration that is of interest. For example, if all the sites are massive MIMO sites with like 64 or 32 antennas, and you have a very large occupied bandwidth, obviously you need to properly scale your processing platform to be able to do that. But this is possible. The question is how scalability is achieved, and the answer is that the scalability is achieved through scaling your processing according to the loading that you have. And then you have these intelligent controllers to make sure that the unused resources are turned off and taken off the network so that they don't contribute to unnecessary energy consumption.
Okay, thank you very much. If there are other questions, kindly just take a look at.
Thanks so much for giving me the opportunity.
Sure.
Appreciate it.